Hi, folks. I initially, okay, let's hope
Uh,
that's, hmm,
Hello, everyone. Today we'll be welcoming Joao. Uh, Currently, is working at DeepMind. So today he'll be presenting his work, uh, which was published at RLC 2024. So yeah, Joao, the floor is all yours.
hey. So in fact, I decided to present something a little bit more general. Um, Let me just see if I can point things. Yeah, okay, a little bit more general than my work. I'll be presenting uh, basically the background to our work and then some other ideas, all of them related to this better empirical research in RL, or maybe how to do better empirical research in RL. And so let's go, I think I'll go here. First of all, let's talk about the prologue, or what the papers that led to a lot of this research, and the matters or the problems with RL. And so they start with this paper here on 2017 called Deep Reinforcement Learning That Matters. And it's a pretty good paper. Um, I reading it, I think it's like, the Silence of the Lambs, Hannibal. It's like you say, oh, that's a pretty good movie. Yeah, this paper is pretty good in the same sense. It's like a horror movie in some ways. Uh, so the paper, both of the publications in, let me just get my pointer. Yeah. Start showing you the growth of publications in RL, especially until like 2015. And they say, okay, we're doing a lot of research in this area, but what is that research concretely, right? And the problem that they were facing that led them to writing this paper was, we need to use RL in the real world. It's not about Atari, Mojoko, or any kind of benchmark. It's like we have a series, I think it was a medical related application, and we want to use RL, and we have questions like how, right? What algorithm are we supposed to use? What neural network architecture, or a bunch of other stuff. And so right from the beginning, they showed this here, which is a plot showing using PPO on the Hafshira environment. And they show different network architectures, and they show that there is like a huge impact depending on the architecture you choose. And this may seem, I don't know, kind of obvious or something like that, but the problem is that what is it saying basically is that when applying deep RL to problems, you start with as many issues, with as many parameters to tune, with as many architectures to search as you would in any kind of supervised problem, right? So all the stuff that you have to do for supervised, you also need to do for RL, but you have other issues. So this is like already a pretty good start. And as they pointed out, especially back in the day, but I think it's still true now, we don't do a lot of ablations or evaluations of different architectures when proposing a new RL algorithm. So we propose it to say, here's an architecture. Is that architecture good? Is it good for our environments? What happens if I change environment? What happens if I try to change architecture? None of that was explored. And it's clearly extremely important when you see how this network here with a layer of 400 neurons and another 300 does extremely worse than just a two-layer 64 neurons per layer network. And then they keep going. As I said, it's like a horror movie. The tension just keeps going up. So now we talk about, again, the half-Shita environment. And we compare a series of actor-critic methods that, frankly, some of them are still popular now, like PPO, but they were the strongest ones at the time. And if you look just here, you see, okay, DDPG seems to be the best one. Maybe like it's close to this AC KTR. Clearly, all of them are better than TRPO. And then you change your environment, and now TRPO is basically at the top, and DDPG is at the bottom. And you look at another environment like the swimmer environment, and you see again the same thing, but now ACKTR is also pretty much at the bottom. And in fact, you have this kind of insane variance of the TRPO performance. So yeah, that again, this raises the question, okay, if I'm trying to do this for a real life problem, for something that will affect people's lives, what do I do, right? What kind of algorithm do I choose? What kind of everything do I choose? And it keeps getting worse. So all of these, again, our dear Hafshita, does anyone know what's the difference between the orange and the blue curves in this first graph? Would anyone like to try? Okay. Okay, someone said learning rates. No, not learning rates. So, as I said, it's a horror movie, right? The difference is the random seeds. So it's the same algorithm. They just ran with 5 different random seeds. So, and you get a difference that if you look at, yeah, exactly. Like it's not just that the averages are different. If you even look at the average plus and minus standard deviation, it still looks like this should be, in some senses, statistically different. But it's the same algorithm. Okay, for the second plot, what do you think is the difference? I will advance. Oh yeah, sorry. There's this. For the second plot, the difference is the code base. With the orange curve, do you see? Yes. So it's 5 seeds for this one and 5 seeds for this other one. So like that's all that's happening here. No, there's no, oh, we're using only one seed a bunch of times, or no, it's like 5 seeds here, 5 seeds here, you get a difference. The second one is the code base. And the funny thing is that for the blue and the orange ones, which have this huge gap in performance, it's the same implementer, with the blue and the, yeah, and the orange one. It's the same person implementing and the author of the algorithm. And just like a difference in code base, and you see a huge gap in performance. And then for the last one, once again, DDPG, now it's a different algorithm. Once again, we just changed the code base and we see another huge gap in performance. And so we get to this, okay, well, now I have to figure out what's a good algorithm, what's a good hyperparameter, and it looks like it's very hard to implement it correctly. The code base, okay, what are the code base changes? Literally different. So when you release a paper, sometimes you open source the code. These are 2 different papers, 2 years apart, by the same people, or at least the same first author. And they release the code for each one of those papers. And if you use TRPO from one of the papers and TRPO from the other code base, they give this different performance. They didn't go into details of all the implementation because that's like no one, okay, very few people know by heart all the implementation details of a specific algorithm. So it's kind of how do you compare so easily, I guess. But yeah, the point is that this shows that even implementing these algorithms like by their own authors is kind of a dicey subject. Okay, and now we're going to go for a quick aside, but that's also going to be related to all of this, which is the TD3 and SAC papers. So these 2 papers are used for mostly continuous control, if I'm not mistaken. They were released in 2018, so a little bit after deep reinforcement learning that matters. And sorry for the silence. And they were released kind of simultaneously, but they ended up like comparing with each other despite that. So here is one of the comparisons. They each have close to 10 comparisons, close to 10 environments. Here's one from the SAC paper. Here's the graph legend. So you can see that at the end of the day, SAC is kind of ahead of TD3, but they are very similar in performance, but a little bit ahead. And then we look at the plot on the TD3 paper, and TD3 here is this blue one, while SAC is this pink one that's extremely below it. And it's kind of peculiar that these two papers come out at the same time and have such a different performances, supposedly. Here you can see them side by side. And once again, here, SAC basically at the top. Here, SAC pretty bad. And yes, this is both for EntV1. And here we go to another environment called Hafshita. And once again, this is the SAC one. SAC is at the top. And in this case, TD3 is again second place. And then we look at the TD3 paper, and TD3 is at the top, and SAC is extremely at the bottom. And you can see it side by side now. And yeah, what's going on? Right? So what the hell is going on here? And so the first thing I think you could note, like if you look just at the paper and you're doing more of a skimming thing, maybe you first read like the DPG part is not very important, but yeah, they explain the paper that they do a couple implementation differences between their DDPG and the original one, but that not very important for this. But okay, so if you look closely, you see that there's like also a difference in scale. Here it goes quite higher than here. And then you can look and see that the number of steps is different. Yeah, the number of steps is different. So in both cases, SAC went all the way to 3 million steps, while TD3 went to 1 million. That's not enough to explain the difference, because if it was, we could just like cut the plots here and they should be basically the same. But once again, SAC is doing pretty well on the SAC paper and is doing bizarrely bad on the TD3 one, right? And again, if you read the paper, the conclusions seems to be in both of them. Like SAC, they say, well, SAC seems to be not worse, and in many cases better than the other algorithms. In TD3, they say TD3 is the best one, it beats everything. And if you look just at the plots, that's what it seems to be implying. Each of them are doing multiple seeds. SAC does 5 seeds, I think. TD3 does 10 seeds. They compare across, I think, close to 10 environments. So it seems to be like a general conclusion, right? Like in general, the SAC is better in one paper. In general, TD3 is better in the other paper. And again, what's going on, right? How can this be? How can we, how can we be happy with a situation like that? And so here is the thing. If you go to the appendix of TD3, there they explain something that I think should be in the main paper. So they say, for fair comparison with our method, we train for only 1 iteration per time step, rather than the 4 iterations used by the results reported by the authors. This is by the authors of SAC. So what is he saying is that on SAC, after every time step, after every iteration with the environment, they then do 4 updates. While during TD3 and when TD3 use the SAC method for comparison, they do only 1 update per interaction, right? And this brings some stuff, some problems here, because that means that those plots indeed are not comparable. This also means that for the TD3 case, they are using a hyperparameter that they probably found out was good for TD3, and they did not test with SAC if that same hyperparameter is good. In the same way, in SAC, if they're just using the TD3 implementation, then that means that SAC tuned that hyperparameter for their algorithm. They chose 4 as the best one for them, and then use only 1 for TD3 instead of trying TD3 with 1 and 4 and a bunch of other values. So this means that all of those plots, they're not doing like a fair comparison between the algorithms. They are tuning some hyperparameters for their own algorithm, but not doing the same tuning for the algorithms they're comparing. Exactly. So Amy Pajak asks, so the issue is no standardized testing comparison across different algorithms or papers? Yes, exactly. That's the problem. They're not standardizing how they do it. And you see that there's another thing here. So on the SAC paper, they say the goal of our experimental evaluation is to understand how the sample complexity and stability of our method compares with prior off-policy and a-policy deep reinforcement learning algorithms. So they care about sample complexity. That's why they're doing 4 iterations per interaction with the environment. And when TD3 compares, they are kind of ignoring that. So now you can really say, okay, maybe if we did 4 to each, SAC would still come out on top. And so from a sample complexity standpoint, they are better. We just can't know because neither of the papers did a fair comparison in that point. Then on TD3, they continued this along with fewer total time steps, which is what we said before. SAC used 3 million or 10 million in some examples, while TD3 always used 1 million. So again, there's a point here, right? TD3 was optimized for this case with 1 million time steps in the Mujoko environments. SAC, they probably optimized it to do pretty well at 3 and 10 million. So the question remains, if we had tried to optimize TD3 to do better at 10 million, maybe we would have seen a different result. If we had optimized SAC to do better at 1 million, maybe again, we would have seen a different result, right? So you can't just take an algorithm with the hyperparameters for a specific data regime, for a specific number of interactions, and just plop it in a different data regime and think like, okay, this is a valid comparison. And then this final part will be relevant for the next paper we talk about, which is, additionally, we note this comparison is against a prior version of Soft Actor Critic, while the most recent variant includes our clipped double Q learning in the value update and produces comparative results to TD3 on both tasks. Again, pretty interesting that they did not say this in the main paper and put it only on the appendix. But also interesting that what does this imply? You know, if SAC becomes something that is always using clip double Q learning, and with that, it ends up being as good as TD3, what was that comparison really? And in some sense, a lot of people in RL used to think that it's like the algorithm decisions, right? The things that are parts of the algorithm itself, and then you have the implementation details. And often you would compare your algorithm to the other algorithm, and that was like the real challenge, the real battle, the real which one is superior. And the implementation details, they're just implementation details, right? And so our next paper, that we are discussing, I have not written any of the previous papers, is precisely about this question of algorithm details and implementation details. And it compares 2 algorithms that are very similar. They are PPO and TRPO. If you read those 2, they start from the same principles. They do a lot of stuff similar. And then basically when they're deciding how to do this proximal optimization, one of them does this in a way and the other does in another. Or basically one of them does a first order approximation, the other does a second order, something like that. And that's the only difference between them a priori, when you just like read the algorithms. But the authors of this paper in 2020, they went looking a little bit into how PPO is implemented in real life, and they started to realize that there are more differences. So PPO does some specific kind of value function clipping, that it's not like what the algorithm in its purity explains. They do a bit of reward scaling, which is also not part of the algorithm as it's written in the paper. They do a different kind of initialization, and they use a specific kind of scaling for each layer of the network, which is again not part of the algorithm. They do a learning rate annealing, which we nowadays call a learning rate schedule for Adam. Again, unsurprisingly, not part of the algorithm. Reward clipping, observation normalization, observation clipping, hyperbolic ternate activations, global gradient clipping. So they have a bunch of things which are implementation details, which are not part of the algorithm, but which they use on PPO and they don't use on TRPO. And then the question arises like, is PPO better because of an algorithmic point, or is it better because of these implementation details? And like, are they really just details if maybe they are the most important part for the difference? Like, okay, maybe even if you use the same details on both, you end up with PPO is still better. But if most of the change comes just from these implementation details, is it okay to call them details, or should they be, part of the real algorithm and maybe even something that we should be studying, right? And so they compare it. They have PPO, they have PPO-M, which maybe should have been just PPO minus, but anyway, which is PPO without all of these improvements. They have TRPO and they have TRPO plus, which is TRPO plus those improvements. Then they define basically the algorithm improvement and the code. I don't remember what the L stands for, but improvements. And this here is the maximum difference between things with the equivalent implementation details, but different algorithms. So they do PPO, the difference between PPO and TRPO plus. They do the difference between PPO-M and TRPO, and then they take the maximum between those two. And for this one here, they compare same algorithm but different implementations. So TRPO, TRPO plus, PPO, PPO-M. And they take the maximum. And what you find across these three different environments is that the different caused by the code changes, by the implementation details, as they call it, is always quite superior to the difference caused by just the algorithm changes. Like here is over 2 times, here is over 4 times, here is a little bit, basically 2 times, right? So this again is a problem, right? Because it means that what we're proposing, what we're saying we're proposing, the things that we are comparing in a more theoretical way, the algorithms, they are not really the most important parts. Maybe the implementation details that we are not proving anything about them, and that we are not ablating them well, and that we're not even describing them in our papers. And you need to have an official code base and go through that code base to really find these details. Maybe those parts matter more than what we've been focusing on. And then there is this blog post that I think was accepted on iClear. That's just, I also love it. It's called the 37 implementation details of proximal policy optimization, where they show that those previous details that we talked about, pretty important. There are a bunch more that without them, you also don't really get a working PPO. So this is not a comparison like the previous paper, but this is mostly then going over all the 37 details that are part of a correct PPO implementation, but which are not described on the paper. And in many ways, this here describes what PPO is quite better than just the PPO paper. Okay, that was the prologue. Now we're going to be talking about the papers that I was part of, and which were, in some sense, our attempt to improve matters a bit. I would say that the previous papers, they are attempts to improve matters, obviously. Deep reinforcement learning that matters is basically what kicked off the notion of we're doing something wrong with RL. And then the paper on implementation matters, shed a light on the question of, okay, these code bases, they also hide a lot of details. And what we're doing here is we're going to be looking specifically at the hyperparameters of value-based algorithms. So our focus here will be more like, okay, we have a bunch of hyperparameters. Let's figure out what's the effect of varying them on some specific algorithms. So the first paper we got out of this is called Lifting the Veil on Hyperparameter for Value-Based Deep Reinforcement Learning. We try to be very specific about what we're doing here. Don't overclaim or anything like that. And we had three main goals with it. So first was looking at how sensitive are the algorithms to variations in hyperparameter selection. Then, does the choice of environment vary that sensitivity? So, another thing is that in many situations, DeepRL was this thing very focused on the algorithms, but maybe like you can't really talk about general performance of an algorithm, and it changes significantly based on the environment. So we're looking at that. And the third one was whether existing methods, if they are underperforming because of some kind of poor hyperparameter choice. And basically, we got some interesting conclusions. We found that there is like some kind of Goldilocks region for network capacity, and that depends on the environment. So again, this shows that the environment is pretty important, and that at least for those algorithms and those network architectures, you can't just go scaling up. Sadly, no, you can't just go scaling laws and be happy. No, if you increase your network too much, you would get pretty reduced performance on some environments. We looked at reward clipping. We saw that the gamma, the discount factor, was also pretty important. And so we got some general high-level conclusions. And we did like plot the sensibility, which did help us see that some specific things like the discount factor or the network width, in different environments, they were extremely important, right? You see things like for Acrobat, basically only the discount factor matters much, but then for Asterix, there's a lot more stuff that matters. So this was like an initial thing. This was just sent to a workshop, and it got us thinking. We decided, okay, we started with this very simple environment, so let's try to go to Atari at least. That will give us more environments, and besides that, let's try to organize this, and instead of just a million plots, let's try to organize this into some kind of metric or something like that. Which led us to our second paper, which was the one accepted to our RLC, which is on the consistency of hyperparameter selection in value-based deep reinforcement learning. Again, not overclaiming anything at all. We even specified value-based, not actor critic or anything like that. Okay, and then what we look here was to look at the transferability, which is related to that notion of sensitivity of these algorithm choices across data regimes. So if I have tuned my hyperparameter in a data regime, my hyperparameters in a data regime, and then I'm going to keep that algorithm, keep the environment, but change the data regime. Do I need to tune those hyperparameters again? Or can I just transfer them like directly and things will work out? Across agents, again, I tune the hyperparameters. Now I'm changing the agent, but I'm keeping the same environment. I'm keeping the same data regime. Can I also keep the hyperparameters, or do I have to tune them? And which one is more consistent versus which one is less consistent? And finally, across environments. So here we keep the algorithm, we keep the data regime, but we change the environment. Which hyperparameters remain consistently good? Which ones we'll have to tune again? Otherwise, you can get pretty poor performance. And this was a long period of a lot of experiments. We did 12 hyperparameters, 2 agents, 5 seeds for 8 agents, 2 data regimes, and 26 environments, which resulted in 108,000 independent training runs. This was a lot. And so this is a lot of information. And even when you just try to plot this and average stuff out, you still have a lot of information. So we ended up like trying to organize this in 2 ways. One of them is we define a new metric, a new score, which will provide some kind of aggregate notion of consistency of the hyperparameters. And we also create a website where you can explore our results in details. I think both of them are pretty cool. The metrics pretty cool. I think the website is also very cool. I think there's a lot of ideas there that can lead to papers. And so, yeah. So first of all, let's talk a little bit about our metric. It's called Tuning Hyperparameter Consistency, or THC. What you do is you pick your setting and you pick a series of hyperparameters, and then for each one of those hyperparameters, you have specific values to it, and you will run a couple of seeds for each one of those values. And from there, you can get some kind of range of performances, right? This one here, I don't recall exactly. It's just an example, really. So let's just imagine that you have a hyperparameter that you experiment with the following values. 10 to the minus 2, 10 to the minus 1, 1, 10, and 100, right? You try those 5 values, you run 5 seeds for each, and you get some kind of performance spread. This here can be many things. It can be literally your minimum and your maximum. This can be something like, oh, I take the average and then I subtract the standard deviation and I add the standard deviation. This can be a 95% confidence interval. In some sense, the metric is open. Like you would have to specify how you're computing this to have an exact metric. Then you get the performances, and we sort them by the mean with breaking ties by the highest value and the lowest value. And you get something like this. So when the hyperparameter was 1, we got the values from 400 to 600. When it was 10 to the minus 1, 250 to 350, and so on. What we do then is we compute new rankings, and they are based on the following. You take a look at what's the best ranking you could get, which is suppose that everyone above you had the worst performance and you had your best performance. So for this value of hyperparameter, the best performance is 300. The ones above, the worst is 250 and 400. So best case scenario, this guy should be on 2nd place. Cool. And then you look at the worst performance that this guy had and at the best of everyone below him and see how far it could fall. So it could fall from 3rd to 4th place. And then you average that. So 1st place, like the minimum is higher than everything. So it's just like first per first. Yeah, the average is C1. The second place, it can't go up, but it could go down if you look at 250 versus 300. So the ranking is 2.5. This one, as you said, could go up to second or fall down to fourth. The average ranking is 3. This one could go up to third, but could not fall below to 5. So average ranking 3.5. And 5 is just too bad. Average ranking keeps on 5. Okay. And so that's how we compute the rankings. Now, what we're going to be looking at is what we do after we have the rankings. So imagine we have the rankings here. Each line here is a ranking in a different environment or a different setting. We are going to be computing the peak-to-peak metric between those environments. So peak-to-peak is maximum minus minimum. So 3 minus 1, 2. 3 minus 2, 1. 3 minus 1, 2. Okay, so what we're looking at here? We're looking at what's the maximum variance in ranking that hyperparameter value had, right? So if a hyperparameter value in a certain setting, a certain environment, for example, could get you to top performance, first place, and in another setting, another environment, for example, it was third place, then the peak to peak will be equal to 2. So that's a pretty high variance in position. And then we normalize. By that we mean we divide by the maximum variability possible, which is the number of hyperparameters minus 1. So in this case, what's the maximum variability? It's 2, because you can go from first place to third place. So we divide by 2, we get 1.0, 0.5, 1.0. And then from the second case here, the peak to peak is 2 minus 1, 1. 2 minus 1, 1, and 3 minus 3, 0. So this guy here was completely consistent. So its peak to peak is just 0. And even when you normalize, it's still just 0. Finally, to compute the THC, you take the average of these values, and then you have the THC for the hyperparameter A1. So 1 plus 0.5 plus 1, 2.5 over 3, that's 0.8333. And then for the hyperparameter B1, like imagine this would be learning rate and weight decay, something like that. It's 0.5 plus 0.5 plus 0 over 3. That's just 0.333. And so from here, what we would say is, in fact, that A1 is less consistent than B1. And why do we say that? Basically because of this notion that a hyperparameter value in A1 that can get you to the top performance could also get you to the bottom performance, and vice versa. While for B1, there is a clear worse value, and the other values, they don't fall too much. So that's the metric we defined. We computed it for many cases. So, and using that, we reached some conclusions. So first of all, optimal hyperparameters mostly transfer across agents. Okay, so here we're comparing basically Rainbow and DQN, slight variations, more data efficient versions of them. And we see that most of the values of the metric, of the score, are pretty low. They're below 0.4. Quite a few of them are literally 0, so they have perfect consistency. Here also perfect consistency. Depending on the data regime, like you can get even more consistency, really. So overall, if you go from something like it's called Dr. Q to DR, which is the data efficient Rainbow, you can mostly not tune the hyperparameters and things will be all right, with some clear exceptions. So batch size and update horizon. And if you look here at some specific cases, at some specific environments, you will see what I mean. So with batch size of 4, you can get the best performance in Asterix and Gopher for, I think this is the ER. But at the same time, you can get the worst performance possible for Battlezone and Kangaroo. In the same way, with a byte size of 32, you can get pretty bad performance at Asterisk and Gopher, and get top performance at Battlezone and Kangaroo. So this is what I mean when I say that the consistency is bad, that metric is high. It means that a value that's really good in one environment can be extremely bad in another. And so the interesting thing is that there's another paper by Pablo and Johan, who are the other co-authors of this paper, who go over basically this idea of, okay, why does reducing batch size can be so good for some algorithms or bad for others, and why this change in the update horizon is also pretty important. So I think in some sense this already shows that this exploration can lead you to finding out some interesting research ideas. Okay, now for another setting, optimal hyperparameters mostly do not transfer across data regimes. And here we say that because we have more values that are above 0.4, and because we have less values that are 0. And so the transfer here is quite worse than the one we saw here. And you can see a couple of examples. So here, same algorithm, we're just changing the learning rate, I believe, learning rate. Here for up to 400,000 frames, and here we go up to 40 million frames. And we see that one of the worst performing values for this case is in fact the best performing by a large margin when you go to the 40 million data regime. And so if you're changing data regimes, you often need to retune the hyperparameters, which goes back to what we talked about on TD3 and SHC. They had a change of data regime, and they did not retune the hyperparameters, which is a problem. And here also, if you look at the ones with the highest values, like update period, on add and epsilon, you'll see also which hyperparameters are the most important for you to be tuning when you change data regime. And again, update period was exactly one of the things that they were not tuning in that one. Anyway. Finally, optimal hyperparameters do not transfer across environments. And this is not a mostly, no, this is a very strong do not. There is not a single 0 in this plot. Most of them, a lot of them are over 0.4. Some of them are basically at 1. So it's like you can go from best to worst performance very commonly by changing the environment. And we can look again at that example that we mentioned before of the asterisk, Battlezone, Gopher, and Kangaroo. Okay. So the main takeaway from the metric is when proposing a new algorithm, please compute the THC of its hyperparameters and vary at least the environment. So, okay, I'm proposing this cool algorithm here, and it's great, and has these hyperparameters. If another person wants to take my algorithm and apply it to their own domain, what are the main hyperparameters that the person needs to tune? They will need to tune something. It's very rare that we have a hyperparameter algorithm that's basically immune to hyperparameters. So please compute THC so at least we know which ones we have to pay the most attention to and which ones we can either ignore or only tune if it's like, okay, we've already got improved performance across everything else. We need more, and you have the compute to do it. And bonus points for doing it when varying the data regime. Also pretty important. Sorry. Data regimes can also tend a lot depending on the environment. So computing these would also be very useful for, okay, you were doing this on Mujoku where you could do 10 million interactions. I am using a real robot for some reason. I can do 1,000 interactions. It's good to know which hyperparameters would be important for me to tune. Okay, and also we have the website. Let's share this tab. It's loading, okay. And here you can look at basically all of our plots and results. You can also look at the GitHub repo. And here you can look at specific metrics like IQM, mean, median. The median is kind of broken, but okay. Optimize the gap. And from here, you can look at the different hyperparameters, and you see results for different agents and different data regimes here. And you can also go to the game comparison, and here you can choose a specific game, and then you can get all the plots for each agent in each data regime, varying every single one of the hyperparameters. And you can also go to hyperparameters in depth, and here you can choose a hyperparameter, and you get your THC score for that hyperparameter for each one of the different data regimes and agents. And then you can look at the environments and compare what different kind of hyperparameters, like how well they do in each one of the environments. So yeah, it's a lot of data. I still believe that a lot of the THC score is what I explained a while ago. Yeah, when I was telling how you can compute this year. And again, these are the THC scores for different for different regimes. Yeah. Oh, sorry, I have shared the tab. Yeah. So THC was what I explained here, and these are the THC values for different hyperparameters when we are varying either the data regime or the agents or the environment. Okay, and now we go to the epilogue. And here, I'll have to just be real quick because it's we're running out of time, and because these papers here, each one is worth at least one presentation. But we have deep reinforcement learning at the edge of the statistical precipice. This is a very important paper for you to do real research, I think, in anything, like not just RL, but it should also be used for supervised learning, LLM stuff. And basically, they go over, here is an example of a plot. They have what are the reported results of the papers, and then they take they run the experiments, and they subsample 100,000 times, and they generate the performance curves. And you see that okay, I'll read this later. And you see that sometimes the reported result is extremely far away, for better or for worse, than what you get from this bootstrapping method. And so they go over all the details of, okay, how can you deal with the fact that we cannot run 100 or 1,000 experiments every time? We can run like 5. How can we get like some statistical certainty of the values that we're talking about? And another very good one is this one called Empirical Design and Reinforcement Learning. This one goes over a million details of how to do empirical research in RL correctly. I like that they do some comparisons also with this notion of RL and doing more like cognitive science on rats and experiments on real animals. And I really like these parts here where they say there's a lot of things to worry about. Just run a good observational study of single agent. But let's gain some perspective here. Why should this be easy? I think it's extremely important. And science is first and foremost about understanding, not picking winners and losers. So if you want to do science, if you want to do research that matters, you should not cut corners. You should not just like, oh, here, my algorithm is better than every other one if I tune it a lot and I don't tune the others, and I use a different setting and I use my own environment. And now that my algorithm is good, I'm going to publish it in Europe, and then I have a lot of publications, and that will be good for my career. No, we need to do research, and research is not easy, and we shouldn't expect it to be. But it's still definitely worthwhile. And thank you. And yeah, any questions? I think, in fact, I saw some of them. Let me try to go there. Okay, Sai, thanks for the nice talk. It would be interesting to check the claims of hyperparameter agnosticism of algorithms like Dreamer v3 and with THC scores. Yep, that definitely makes sense. And that definitely will be something that will be interesting to check. They do a lot of tricks targeted at making the algorithm H-parameter agnostic, at least to the extent that the same parameters work for Atari, Minecraft. Yeah, that's very interesting. Great. Hopefully they are doing a real work that, like, yeah, these things are agnostic. But it would also be interesting to have THC scores for when they change the data regime, for example, or even, okay, like the paper came out saying that it's hyperparameter agnostic for these environments. Let's take an environment that did not test. Is it still hyperparameter agnostic? Because, sometimes we may just have like tune the hyperparameters for a larger set of environments, but then as soon as you get out of the sets, the things don't work. Where can we get a list of the papers you recommend here? I was wondering if you have your own web page. I will send the slides. I'm pretty bad at maintaining my web pages, so I'll just send the slides for you. And yeah, I'll share it. Let me just. So I think all the slides basically say that it's confidential when it's not confidential. So I just need to like delete that part or maybe change the. Yeah. Once I have fixed that part, I will share the slides. I just messed up a little bit with that. Yeah.
Hello. Hello.
Yeah, I can hear you. I can hear you. It seems like Joe is disconnected.
Hi, sorry, my internet is kind of unstable. Thankfully, I managed to give the rest of the talk with no problems. Can you hear me? Okay.
Yep, we can hear you. We can hear you.
Was there any other question?
The last question is about someone is asking about the slides and maybe Streamlit app. Maybe you can share it in the group. Joe?
Okay. Sorry,
Yeah.
I had explained all of that, but probably the call had already gone down. I will share with you the slides. I just need to remove something real quick. That's
Sure.
I accidentally didn't remove there's a thing called saying confidential in all the slides. They are not confidential, but I forgot to remove that, so I need just to fix it and then I'll share. And the Streamlit link will be on the slides, but I can also share it here.
Thank
Okay.
you, Joao. Joao.
Yeah, thanks for the opportunity.
Thank you so much.
Thank you, Joe.
Okay, bye.
Nice to see you back.